The James Webb Space Telescope, that magnificent eye we've placed at the edge of our cosmic neighborhood, has been sending back images and data that have left the world's most brilliant astrophysicists staring at their computer screens in stunned silence. What they're seeing isn't just surprising, it's universe-shattering in the most literal sense imaginable. For decades, we've carried a mental map of cosmic history, a timeline that felt solid, well understood, almost comfortable in its predictability. The universe began with the Big Bang 13.8 billion years ago. For hundreds of millions of years, darkness reigned as the first atoms formed, and gravity slowly, patiently, began its ancient work of pulling matter together. Then gradually, the first stars flickered to life. Eventually, these stars gathered into the first galaxies, small and primitive compared to the magnificent spiral structures we see today. This timeline painted a picture of a universe that took its time, that followed the rules we expected, that grew from simplicity to complexity in measured, understandable steps. It was a cosmic story that made sense, that fit neatly into our mathematical models and theoretical frameworks. But Webb has shattered this comfortable narrative completely. When the telescope first began sending back data from the deepest reaches of space and time, astronomers expected to see exactly what our models predicted: small, faint, primitive galaxies struggling to form in the cosmic dawn. Instead, they found something that shouldn't exist. Massive, brilliant, fully formed galaxies blazing with the light of billions of stars, existing at times when the universe was barely 300 million years old. To put this in perspective, imagine expecting to find a few scattered seeds in freshly tilled soil, only to discover a fully mature forest with ancient trees reaching toward the sky. These galaxies aren't just slightly larger than expected. They're so massive, so bright, so impossibly complex that they've forced scientists to question whether our fundamental understanding of how the universe works might be completely wrong. The galaxy designated JD's GSZ 14-0 stands as perhaps the most shocking discovery of all. This cosmic giant stretches across more than 1,600 light-years and burns with the radiance of countless stellar furnaces. But here's what makes it truly extraordinary. The light we're seeing from this galaxy began its journey toward us when the universe was only 2% of its current age. 2%. Think about what that means for a moment. If the entire history of the universe were compressed into a single year, we're looking at galaxies that existed in early January, when everything should have been dark, cold, and empty. Instead, we're seeing a cosmic metropolis in full bloom, teeming with stellar activity and complex structures that our models say should have taken billions of years to develop. The implications ripple outward like waves in a cosmic pond. If galaxies this massive and complex could form so quickly, what does that say about the fundamental processes that govern cosmic evolution? How did gravity work so efficiently in the early universe? How did gas collapse into stars at rates that dwarf anything we see today? How did supermassive black holes, objects containing millions of times the mass of our Sun, come into existence when the universe was still in its cosmic infancy? These aren't just minor adjustments to our understanding. These discoveries are forcing us to reconsider the very foundations of cosmology itself. The abundance of these early giants has created what scientists are calling a crisis in cosmology. Computer simulations that successfully model the universe we see today simply cannot account for the rapid formation of such massive structures in the primordial cosmos. The universe appears to have been far more efficient at building galaxies in its youth than our most sophisticated theories suggest should be possible. But Webb's revelations extend far beyond just finding big galaxies in unexpected places. The telescope has detected something even more mysterious: supermassive black holes lurking at the hearts of these ancient galaxies, gorging themselves on surrounding matter and growing to impossible sizes in impossibly short timeframes. The galaxy GN-Z11, observed when the universe was only 430 million years old, harbors a central black hole that's actively feeding on the gas and dust around it. The very existence of such a massive object so early in cosmic history challenges everything we thought we understood about how black holes form and grow. These aren't the stellar mass black holes that form when massive stars collapse. These are cosmic behemoths that somehow achieved millions of solar masses when the universe had barely begun its story. The mystery deepens when we consider the relationship between these early black holes and their host galaxies. Today, we observe a delicate balance between the mass of a galaxy's central black hole and the mass of stars in the galaxy's central region. This relationship suggests that galaxies and their central black holes grew together over cosmic time, each influencing the other's development in a cosmic dance of mutual evolution. But how could this relationship have been established so early in the universe's history? How did these black holes and galaxies achieve such perfect synchronization when there simply hadn't been enough time for the slow, gradual processes we observe today? Webb has also revealed something equally puzzling about the chemical composition of these ancient galaxies. When we look at the spectrum of light coming from JADES GS-Z14-0, we see clear evidence of oxygen and other heavy elements that could only have been forged in the nuclear furnaces of massive stars. But the presence of these elements so early in cosmic history presents another timeline problem. Heavy elements are created when massive stars live their brief, violent lives and then explode as supernovae, scattering their nuclear ashes into space where they can be incorporated into the next generation of stars and planets. This process of stellar nucleosynthesis and chemical enrichment should take hundreds of millions of years to produce detectable amounts of heavy elements. Yet here we are, seeing clear signatures of these elements in galaxies that existed when the universe was still a cosmic toddler. Either stars in the early universe lived and died much faster than we thought possible, or multiple generations of stars had already come and gone in the time we thought it took for the first stars to form. The scale of these revelations becomes even more staggering when we consider how Webb makes these observations. The telescope doesn't just look across vast distances of space, it literally looks backward through time itself. Light from these ancient galaxies has been traveling toward us for more than 13 billion years, carrying with it a message from an epoch when the universe bore no resemblance to the cosmos we inhabit today. This light has been stretched and redshifted by the expansion of the universe itself, its wavelengths elongated by factors of 15 or more as space itself has grown larger during the light's epic journey. What began as ultraviolet radiation from hot young stars has been transformed into infrared light that only Webb's exquisitely sensitive instruments can detect and decode. The technical achievement required to capture and interpret these cosmic whispers is nothing short of miraculous. Webb orbits the Sun at a distance of 1.5 million kilometers from Earth positioned at a gravitational balance point where it can maintain a constant view of deep space while remaining thermally stable. Its 5-layer sunshield provides protection equivalent to sunblock with an SPF rating of 1 million, allowing its instruments to operate at temperatures just above absolute zero. This extreme engineering enables Webb to detect the faintest glimmers of light from the cosmic dawn, photons that have traveled unimaginably vast distances to reach its mirrors. Each observation represents the culmination of decades of technological development and scientific planning, transforming ancient starlight into digital data that reveals the secrets of our cosmic origins. But perhaps the most profound implication of Webb's discoveries is what they suggest about the true scale of cosmic evolution. If the universe could create such complex structures so quickly in its youth, what marvels might exist in regions of space and time that remain beyond our current observational reach? How many more surprises await us as Webb continues to peer deeper into the cosmic past? The telescope's observations have already extended our view of cosmic history by 40% in just its first 18 months of operation. We've pushed back the boundaries of the observable universe, revealing epochs of cosmic evolution that we previously could only imagine. And with each new observation, with each record-breaking discovery, we're forced to confront the humbling reality that the universe is stranger, more wonderful, and more magnificent than our theories had dared to suggest. Tonight, as you rest under the same cosmic canopy that has witnessed the entire sweep of galactic evolution, remember that you're part of this grand story. The atoms in your body were forged in stellar cores, not unlike those burning in the galaxies Webb observes across the vastness of space and time. You are quite literally made of star stuff, a temporary arrangement of cosmic matter that has achieved the remarkable ability to contemplate its own origins and place in the infinite expanse of existence. These discoveries have unveiled something even more extraordinary lurking within the data streams flowing back from Webb's position in the cosmic void. The telescope hasn't just found galaxies where they shouldn't exist. It has revealed that these ancient stellar cities display a diversity and complexity that defies every prediction about what the early universe should have looked like. Consider the mysterious objects that blur the very boundaries of how we classify cosmic structures. Webb has detected luminous, enigmatic entities in the primordial cosmos that seem to exist in a strange twilight zone between galaxies and something else entirely. These objects pulse with characteristics of both supermassive black holes and ancient stellar populations, creating a cosmic riddle that has left astronomers scratching their heads in wonder. Imagine discovering what appears to be a library that somehow contains both brand new books and ancient texts that predate the invention of writing itself. This is precisely the paradox these mysterious objects present. They display the signatures of old, evolved stellar populations alongside the violent energy signatures of actively feeding black holes. The light reaching us suggests these structures might be galaxies more massive than our own Milky Way, yet existing when the universe was only 5% of its current age. The implications stretch far beyond simple questions of when things formed. These discoveries are forcing us to reconsider the fundamental processes that govern how matter behaves in the cosmic arena. In our local universe, galaxies follow predictable patterns of growth and evolution. Star formation proceeds at measured rates. Black holes grow gradually over billions of years. and chemical elements accumulate slowly through successive generations of stellar death and rebirth. But the early universe appears to have operated under entirely different rules. Star formation rates in these primordial galaxies rival or exceed those of the most active star-forming regions we observe today. Gas seems to have collapsed into stellar nurseries with an efficiency that makes our current models appear woefully inadequate. The very fabric of space and time seems to have facilitated processes that we struggle to comprehend using our present understanding of cosmic physics. Webb's observations have revealed that the so-called dark ages of the universe, that supposedly quiet period between the formation of the first atoms and the birth of the first stars, may not have been dark at all. Instead of a cosmic winter lasting hundreds of millions of years, we're seeing evidence that the universe began its stellar awakening much earlier than anyone dared imagine. The ultraviolet light from these early stellar giants would have begun the process of reionization, breaking down the neutral hydrogen that filled space and fundamentally altering the cosmic environment. This process, which we thought began gradually around 400 million years after the Big Bang, appears to have commenced far earlier, driven by populations of massive, luminous stars that shouldn't have existed yet. Each new observation from Webb reads like a cosmic detective story, with clues that point toward a universe far more dynamic and complex than our comfortable theories suggested. The redshift measurements, those cosmic fingerprints that tell us how far back in time we're looking, have reached values that seemed impossible just a few years ago. Light stretched by factors approaching 15, wavelengths elongated by the relentless expansion of space itself over cosmic epochs. Think about the journey these photons have undertaken. They departed their stellar birthplaces when the universe was a radically different place, traveled through expanding space for over 13 billion years, survived the cosmic expansion that stretched their wavelengths from ultraviolet to infrared, and finally encountered Webb's precisely engineered mirrors in our modern epoch. Each photon carries within its electromagnetic signature the story of cosmic conditions that existed when reality itself was young and wild. The precision required to decode these ancient messages borders on the miraculous. Webb's instruments must distinguish between photons that originated in different cosmic epochs, separate the light of distant galaxies from foreground contamination, and extract meaningful scientific information from signals so faint they represent mere handfuls of particles arriving at the telescope after their epic journey across space and time. The observational campaigns required to make these discoveries demand extraordinary commitments of telescope time and computational resources. Individual observations can require days of continuous monitoring, with Webb's instruments locked onto targets so distant and faint that even the slightest vibration or thermal fluctuation could compromise the data. The survey that discovered the current distance record holder required over 200 hours of combined imaging time, focused on a patch of sky smaller than a grain of sand held at arm's length. Yet within these seemingly empty patches of cosmic real estate, Webb has revealed entire populations of galaxies that existed when the universe was in its infancy. The statistical implications are staggering. If such massive luminous galaxies can be found in the tiny volumes of space that Webb has surveyed so far, how many more must exist in the vast regions of the early universe that remain unexplored? Extrapolating from these early discoveries suggests that the primordial cosmos was teeming with galactic activity on scales we never imagined. Instead of a sparse, quiet universe gradually awakening from its post-Big Bang slumber, we're seeing evidence of a cosmic environment that was vibrant, active, and astonishingly productive, almost from the very beginning of cosmic time. The abundance of bright early galaxies has created ripple effects throughout multiple areas of astronomical research. Models of cosmic chemical evolution must now account for the rapid production and distribution of heavy elements in the early universe. Theories of supermassive black hole formation must explain how these cosmic giants achieved their enormous masses in timeframes that seemed impossibly brief. Our understanding of cosmic ionization must incorporate the effects of stellar populations that began shining hundreds of millions of years earlier than expected. But perhaps most profoundly, Webb's discoveries are reshaping our perception of cosmic time itself. The universe we observe today is the product of nearly 14 billion years of evolution, a vast span that encompasses countless generations of stellar birth and death, the formation and destruction of countless worlds, and the slow accumulation of complexity that led ultimately to our own existence. Yet Webb is showing us that many of the processes we assumed required billions of years to unfold actually occurred in cosmic timeframes that seem almost instantaneous by comparison. Massive galaxies assembled themselves in hundreds of millions of years rather than billions. Supermassive black holes achieved their titanic proportions while the universe was still a cosmic infant. Chemical elements that we thought required multiple generations of stellar evolution appeared in the cosmic environment almost immediately after the first stars ignited. This acceleration of cosmic evolution doesn't just change our timeline of when things happened. It fundamentally alters our understanding of how efficiently the universe can transform simple matter into complex structures. The early cosmos appears to have been a far more productive and dynamic place than our theories suggested, capable of achievements that push against the very limits of what physics allows. The mystery deepens when we consider that these rapid evolutionary processes seem to have slowed down significantly as the universe aged. The galaxies we observe in our cosmic neighborhood grow at much more sedate rates. Their central black holes accumulate mass gradually over billions of years, and star formation proceeds at measured paces that our models can successfully predict. Why did the universe become less efficient at building massive structures as it aged? What changed in the cosmic environment that caused these dramatic evolutionary processes to slow down? Was there something special about the physical conditions in the early universe that facilitated rapid galaxy formation? Or are we missing fundamental pieces of the cosmic puzzle? These questions touch on some of the deepest mysteries in cosmology. They challenge our understanding of dark matter, that invisible scaffolding that provides the gravitational framework upon which visible matter assembles. They probe the nature of dark energy, the mysterious force driving cosmic acceleration. They even raise questions about whether our basic understanding of gravity itself might be incomplete on cosmic scales. Webb's observations continue to accumulate with each passing month, each new dataset potentially containing discoveries that could reshape our cosmic worldview once again. The telescope's planned mission duration spans many years, promising continued revelations that will push our understanding of the universe into territories we can barely imagine. Tonight, as photons from distant stars and galaxies rain down upon Earth carrying messages from cosmic epochs we're only beginning to understand, remember that you're witnessing one of the most extraordinary chapters in the history of human discovery. We stand at the threshold of a new cosmic age, equipped with tools that allow us to peer deeper into space and time than ever before, revealing a universe that continues to surprise and humble us with its magnificent complexity. As these cosmic revelations continue to unfold before our eyes, Webb has uncovered something even more profound about the fundamental nature of reality itself. The telescope's observations are revealing that our universe operates according to principles we're only beginning to glimpse, principles that govern how matter and energy dance together across the vast stage of space-time. The precision of Webb's measurements has eliminated long-standing uncertainties that have plagued cosmology for decades. When astronomers measure the distances to faraway galaxies, they rely on cosmic lighthouses called Cepheid variable stars, stellar beacons that pulse with predictable rhythms. But these stellar heartbeats become increasingly difficult to detect as we peer deeper into space, their signals potentially contaminated by neighboring stars or dimmed by interstellar dust. Webb's extraordinary sensitivity has cut through these observational challenges like a cosmic scalpel, providing measurements so precise they've confirmed what many scientists suspected but couldn't prove. The universe is expanding at a rate that doesn't match our most sophisticated theoretical models. This discrepancy, known as the Hubble tension, represents one of the most significant puzzles in modern astrophysics. Imagine discovering that your carefully calibrated watch consistently runs fast compared to every other timepiece in existence. You might suspect your watch is broken, but what if every other measurement you make confirms its accuracy? This is precisely the situation cosmologists find themselves in today. Two independent methods of measuring cosmic expansion yield different answers, and Webb's observations have confirmed that the discrepancy is real, not the result of measurement errors. The implications extend far beyond academic curiosity. If our standard model of cosmology cannot account for the universe's current expansion rate, then perhaps our understanding of reality itself remains fundamentally incomplete. The cosmos might harbor unknown forms of energy or matter that we haven't discovered yet. The very laws of physics that govern cosmic evolution might operate differently on the largest scales than our theories predict. Webb has also revealed the extraordinary chemical complexity that existed in galaxies when the universe was still learning how to make stars. The presence of oxygen and other heavy elements in these ancient stellar nurseries tells a story of cosmic alchemy that unfolded at breathtaking speed. These elements could only have been forged in the nuclear furnaces of massive stars, then scattered into space when those stars met their violent ends in supernova explosions. But the timeline required for this cosmic chemistry creates another puzzle that challenges our understanding. Multiple generations of massive stars must have lived, died, and enriched their galactic environments with heavy elements in timeframes that seem impossibly brief. Either these primordial stars evolved much faster than their modern counterparts, or the early universe was far more efficient at recycling stellar material than our models suggest. The diversity of structures that Webb observes in the cosmic dawn reveals a universe that was experimenting with different architectural styles almost from the moment construction began. Some early galaxies appear as compact powerhouses, dense concentrations of stellar activity burning with the intensity of cosmic furnaces. Others stretch across vast distances, their stars spread throughout regions larger than many modern galaxies. This structural variety suggests that the processes governing galaxy formation in the early universe were far more complex and chaotic than the orderly scenarios our simulations typically produce. Instead of following predictable patterns, cosmic evolution appears to have proceeded through a series of experiments with different regions of space trying different approaches to assembling matter into gravitationally bound structures. The supermassive black holes that Webb has detected at the hearts of these ancient galaxies present perhaps the most mind-bending puzzle of all. These cosmic giants contain masses equivalent to millions of our suns, yet they achieved these titanic proportions when the universe was barely out of its infancy. The challenge isn't just explaining how they grew so large so quickly, but understanding how they formed in the first place. Current theories suggest that supermassive black holes begin as stellar mass objects, perhaps a few dozen times heavier than our Sun, then gradually accumulate matter over billions of years. But this gradual growth process simply cannot account for the giants Webb observes in the early universe. They would need to have been feeding continuously at the maximum possible rate, never pausing in their cosmic feast. And even then, the timeline remains uncomfortably tight. Alternative scenarios propose that these black holes might have formed through entirely different mechanisms in the primordial universe. Perhaps they began as primordial black holes, cosmic remnants from the Big Bang itself. Or maybe they formed through the direct collapse of massive gas clouds in the early universe, bypassing the stellar formation phase entirely. Each possibility requires exotic physics operating under conditions we can barely imagine. The relationship between these early supermassive black holes and their host galaxies reveals another layer of cosmic mystery. In the present-day universe, we observe a tight correlation between the mass of a galaxy's central black hole and the mass of stars in the galaxy's central region. This relationship suggests that galaxies and their central black holes grew together over cosmic time, each influencing the other's development through gravitational interactions and energetic feedback. But how could such a delicate relationship have been established so early in the universe's history? The coordination required between galactic and black hole growth implies a level of cosmic organization that seems remarkable for such a young universe. Either these relationships emerged much faster than we thought possible, or they represent fundamental aspects of how matter organizes itself under the influence of gravity. Webb's observations have also revealed unexpected patterns in how early galaxies cluster together across space. Rather than being randomly scattered throughout the primordial cosmos, these ancient stellar cities show signs of already being organized into the cosmic web. That vast network of filaments and voids that characterizes the large-scale structure of the universe today. This early emergence of cosmic organization suggests that the universe began developing its architectural framework much sooner than anticipated. The gravitational processes that shape the cosmic web, drawing matter along invisible highways of dark matter, appear to have been operating with surprising efficiency in the cosmic dawn. Instead of a gradual evolution from chaos to order, we're seeing evidence of rapid self-organization on the largest scales imaginable. The technical achievements required to make these observations represent triumphs of human engineering and ingenuity that border on the miraculous. Webb's instruments can detect individual galaxies so distant and faint that their light has been traveling toward us for over 90% of the universe's entire history. The photons reaching the telescope carry information encoded in their wavelengths, polarization, and arrival times, cosmic messages that reveal the physical conditions existing in stellar nurseries when the universe was radically different from today. Each observation requires exquisite coordination between multiple systems operating at the very limits of current technology. The telescope must maintain its precise pointing while orbiting the Sun at tremendous speeds. Its instruments must distinguish between signals separated by tiny fractions of electromagnetic wavelengths, and its data processing systems must extract meaningful scientific information from signals so weak they represent just handfuls of particles arriving after their epic journey across space and time. The observational campaigns that yield these record-breaking discoveries often require weeks or months of planning, followed by days of continuous observations, as Webb locks onto targets for extended periods. The galaxy surveys that have revealed the most distant objects known to science represent investments of hundreds of hours of telescope time, focused on regions of sky so small they would be covered by a grain of sand held at arm's length. Yet within these seemingly empty patches of cosmic real estate, Webb continues to discover entire populations of galaxies that challenge our fundamental assumptions about cosmic evolution. The statistical implications suggest that the early universe was far more densely populated with massive active galaxies than our theories predicted. If such objects exist in the tiny volumes of space Webb has surveyed, the total population of early galaxies throughout the observable universe must number in the billions or trillions. This abundance of early galactic activity has profound implications for our understanding of cosmic ionization, the epoch when the first stars and galaxies began to clear the fog of neutral hydrogen that filled space in the aftermath of the Big Bang. Instead of a gradual process driven by relatively few faint sources, ionization appears to have been powered by vast populations of luminous galaxies that began shining much earlier than expected. The energy output from these early stellar populations would have fundamentally altered the cosmic environment, heating and ionizing the gas between galaxies and setting the stage for all subsequent cosmic evolution. The universe transitioned from opacity to transparency, not through a gentle dawn, but through a cosmic revolution driven by stellar populations whose existence rewrites our understanding of when and how the cosmic dark age ended. Webb's continuing observations promise even more dramatic discoveries as the telescope pushes deeper into cosmic history. The current distance records represent just the beginning of our exploration of the primordial universe. Future observations will probe even earlier epochs, potentially revealing the very first generation of stars and galaxies to emerge from the cosmic dark. Each new discovery adds another piece to the cosmic puzzle, yet simultaneously reveals how much we still don't understand about the universe's magnificent complexity. We stand at the threshold of a new era in cosmology, equipped with tools that allow us to witness cosmic history unfolding across scales of space and time that dwarf human imagination. Tonight, as ancient starlight continues its journey across the cosmos to reach our world, carrying messages from epochs when reality itself was young and wild, remember that you're part of this ongoing story of discovery. The quest to understand our cosmic origins connects us to something far grander than our individual lives, revealing our place in a universe that continues to surprise and humble us with its extraordinary beauty and complexity. These discoveries have revealed something even more extraordinary about the very fabric of reality itself. Webb's observations are showing us that the universe operates according to a cosmic architecture so elegant and interconnected that every discovery seems to unlock new chambers in an infinite cathedral of knowledge. The telescope has detected gravitational waves frozen in light, cosmic ripples that reveal how space-time itself was sculpted during the universe's infancy. When massive objects in the early universe merged and collided, they sent waves through the very geometry of reality, distortions that Webb can now read like cosmic hieroglyphs etched into the background radiation that permeates all of space. These gravitational signatures tell us that the early universe was far more violent and dynamic than our peaceful models suggested. Cosmic collisions that would dwarf anything we observe today were commonplace in the primordial cosmos. As massive objects crashed together with energies that stagger the imagination, the universe wasn't gradually assembling itself through quiet accretion, but was forged in a series of titanic impacts that shaped the fundamental structure of reality itself. But perhaps the most profound revelation emerging from Webb's data concerns the nature of time itself in cosmic evolution. The telescope isn't just showing us that things happened faster than expected. It's revealing that time might flow differently in the presence of the extreme gravitational fields that dominated the early universe. Einstein's theory of relativity tells us that time is not a universal constant, but a flexible dimension that bends and warps in the presence of massive objects. Near black holes, time slows to a crawl compared to regions of weaker gravity. In the early universe, when matter was compressed into densities we can barely comprehend, time itself might have operated according to entirely different rules. Consider the implications of this temporal flexibility for cosmic evolution. If time flowed differently in the dense environments where the first galaxies formed, then processes we assume required billions of years might have unfolded in relative moments from the perspective of the evolving structures themselves. The universe might have experienced its own internal acceleration, with cosmic evolution proceeding according to relativistic time dilation effects that our models have never accounted for. Webb has also uncovered evidence of cosmic recycling on scales that challenge our understanding of how matter flows through the universe. The heavy elements detected in early galaxies didn't just appear through stellar nucleosynthesis and supernova explosions. They show patterns suggesting that matter was being efficiently transported between galaxies, shared across cosmic distances, through processes we're only beginning to understand. Imagine discovering that the early universe operated like a vast circulatory system, with currents of enriched material flowing between galactic clusters along invisible highways of dark matter. Gas enriched with heavy elements in one region could travel vast distances to seed star formation in entirely different cosmic neighborhoods, creating a level of chemical connectivity that transforms our picture of galactic evolution. This cosmic circulation system would explain how chemical complexity spread so rapidly through the early universe, but it also suggests that galaxies weren't isolated islands of star formation, but connected components of a larger cosmic organism. The universe was coordinating its own chemical evolution, sharing resources across distances that span significant fractions of the observable cosmos. The precision of Webb's spectroscopic observations has revealed another layer of mystery in the form of isotopic ratios that shouldn't exist in early galaxies. Isotopes are variants of chemical elements with different numbers of neutrons, and their relative abundances tell us about the nuclear processes that created them. In normal stellar evolution, these ratios change predictably as successive generations of stars process, and reprocess cosmic material. But Webb is detecting isotopic signatures in early galaxies that suggest nuclear processes were operating under conditions completely unlike anything we observe today. Either the stars of the primordial universe burned with nuclear fires that operated according to different physical principles, or alternative mechanisms were at work that we haven't yet identified. Some researchers speculate that these unusual isotopic patterns might be signatures of primordial black hole formation, cosmic events so energetic they could alter nuclear processes in ways that leave detectable fingerprints billions of years later. Others suggest they might indicate the presence of exotic matter states that existed only in the extreme environments of the early universe, before the cosmos cooled and expanded to its present configuration. The structural complexity that Webb observes in early galaxies extends beyond simple questions of size and brightness to reveal organizational principles that seem to emerge spontaneously from cosmic chaos. These ancient stellar cities display spiral arms, central bulges, and satellite structures that mirror the galactic architecture we see today. Yet they achieved this complexity when the universe had barely begun its expansion. This rapid emergence of galactic structure suggests that the universe possesses inherent organizational tendencies that operate on timescales far shorter than we imagined. Like crystals forming in a supersaturated solution, cosmic matter appears capable of spontaneously assembling itself into complex configurations under the right conditions. Guided by physical principles we're only beginning to comprehend. The magnetic fields that Webb detects in early galaxies present another puzzle that challenges our understanding of cosmic magnetism. These invisible force fields, which play crucial roles in star formation and galactic evolution, somehow achieved strengths and organizations comparable to modern galaxies, despite the youth of their host systems. Magnetic fields typically require time to build up through dynamo processes driven by rotating matter. Yet these early examples appear fully developed almost from the moment their galaxies formed. This magnetic precocity suggests that the early universe might have been threaded with primordial magnetic fields, cosmic-scale force lines that provided the seeds for the complex magnetic architectures Webb observes today. These fields could have guided the flow of matter during galaxy formation, channeling gas and dust into the organized structures that became the first stellar nurseries. Webb's observations have also revealed unexpected connections between the most distant galaxies and phenomena we observe in our local cosmic neighborhood. Chemical signatures detected in primordial galaxies match patterns found in ancient star clusters within our own Milky Way, suggesting that the processes governing early cosmic evolution continue to influence stellar formation today. These connections imply that the universe possesses a kind of cosmic memory, preserving information about its earliest epochs within structures that persist to the present day. Like geological strata that record Earth's ancient history, stellar populations throughout the cosmos carry chemical and structural fingerprints that encode the story of cosmic evolution stretching back to the universe's infancy. The energy sources that power the luminous early galaxies detected by Webb present yet another mystery that pushes against the boundaries of known physics. Some of these ancient stellar cities shine with luminosities that exceed what normal stellar populations can produce, even accounting for the most optimistic assumptions about star formation efficiency and stellar mass distributions. These superluminous early galaxies might be powered by exotic energy sources that operated only in the primordial universe, when physical conditions were radically different from today. Perhaps they harbor populations of massive stars, unlike anything that forms in the modern cosmos. Stellar giants that burn with nuclear fires so intense they dwarf even the most extreme examples we observe today. Alternatively, these luminous early galaxies might be revealing the signatures of dark matter interactions that were more prominent in the dense environments of the early universe. If dark matter particles were capable of annihilating each other or undergoing other exotic interactions under primordial conditions, the energy released could contribute significantly to the luminosity of early galactic systems. The clustering patterns that Webb observes among early galaxies reveal a cosmic web that was already remarkably well developed when the universe was less than 1 billion years old. Instead of random distributions of isolated objects, these ancient galaxies show clear evidence of organization into filaments, walls, and voids that mirror the large-scale structure of today's universe. This early emergence of cosmic architecture suggests that the gravitational processes responsible for the cosmic web operated with unexpected efficiency in the primordial universe. Dark matter, that invisible scaffolding that provides the framework for all cosmic structure, must have assembled itself into the complex network we observe today far more rapidly than our simulations predict. The implications extend beyond mere structure formation to touch on fundamental questions about the nature of dark matter itself. If this mysterious substance could organize itself so efficiently in the early universe, it might possess properties or interaction mechanisms that remain hidden under present-day conditions, but were prominent when matter densities were much higher. Webb's continuing surveys are revealing that early galaxies exist in even greater abundances than the first discovery suggested. Each new observation pushes the boundaries of the observable universe further back in time, uncovering populations of primordial galaxies that existed when cosmic conditions were even more extreme than previously explored. The statistical implications of these discoveries suggest that the early universe was absolutely teeming with galactic activity. If Webb can detect massive, luminous galaxies in the tiny patches of primordial space it has surveyed so far, the total population of early galaxies throughout the observable universe must represent one of the most spectacular episodes of cosmic construction in the history of reality itself. These revelations are forcing astronomers to reconsider not just when galaxies formed, but how the universe as a whole evolved from the simple, nearly uniform conditions that existed shortly after the Big Bang to the complex, richly structured cosmos we inhabit today. The transition from cosmic simplicity to galactic complexity appears to have occurred far more rapidly and efficiently than any of our theories predicted. The mystery deepens when we consider that this explosive phase of cosmic evolution seems to have slowed dramatically as the universe aged. The galaxies we observe in our local cosmic neighborhood grow at much more sedate rates, assembling their stellar populations gradually over billions of years, rather than the frantic timescales that characterize the cosmic dawn. Something fundamental about the cosmic environment changed as the universe expanded and cooled, transforming it from a realm of rapid galactic construction to the more leisurely evolutionary pace we observe today. Understanding this transition represents one of the greatest challenges in modern cosmology, requiring us to identify the physical processes that governed cosmic evolution during its most dynamic epochs. Webb's observations continue to accumulate with each passing month, each new dataset potentially containing discoveries that could reshape our understanding of reality itself. The telescope's extraordinary sensitivity and unprecedented infrared capabilities ensure that we're only seeing the beginning of revelations that will unfold over the coming years and decades. Tonight, as you rest beneath the cosmic canopy that has witnessed the entire sweep of galactic evolution, remember that Webb's discoveries are more than astronomical curiosities. They're revealing the fundamental principles that govern how complexity emerges from simplicity, how order arises from chaos, and how the universe transforms simple matter into the magnificent structures that fill the cosmic arena. The story Webb is telling us isn't just about distant galaxies and ancient black holes. It's about the creative capacity of the universe itself, the remarkable ability of cosmic matter to organize itself into increasingly complex and beautiful forms across scales that span from subatomic particles to galactic superclusters. We stand witness to a cosmic renaissance of understanding, equipped with tools that allow us to peer into the universe's deepest secrets and witness the magnificent processes that shaped everything we see around us. Each photon reaching Webb's mirrors carries within it a piece of this grand cosmic story, ancient light that connects us directly to the epochs when reality itself was young and the future of the universe hung in the balance. As we drift deeper into Webb's cosmic revelations, something even more profound begins to emerge from the data streams flowing back across the void. The telescope isn't just rewriting our timeline of cosmic evolution. It's revealing that the universe operates according to principles so elegant and interconnected that each discovery unlocks new chambers in an infinite cathedral of cosmic truth. The wavelengths of ancient starlight carry more than just photons across the cosmic dark. They transport information encoded in patterns so subtle that only Webb's exquisite sensitivity can decode their meaning. Within these electromagnetic whispers lies evidence of phenomena that challenge our most fundamental assumptions about how reality assembles itself from the quantum foam of existence. Consider the magnetic architecture that Webb has detected threading through primordial galaxies, like invisible spider webs spanning cosmic distances. These force fields, essential for guiding star formation and channeling the flow of cosmic matter, somehow achieved organizational complexity that rivals anything we observe in the modern universe. Yet they accomplished this feat when the cosmos was barely 3% of its current age. Magnetic fields typically require eons to develop their intricate structures through dynamo processes powered by rotating matter and electrical currents. But Webb is showing us galactic magnetic systems that appear fully formed almost from the moment of their birth, as if the early universe possessed some hidden mechanism for rapidly organizing these invisible force lines into complex functional networks. The implications ripple outward like gravitational waves through our understanding of cosmic physics. Perhaps the primordial universe was threaded with magnetic fields that emerged directly from the Big Bang itself, cosmic-scale force lines that provided ready-made frameworks for the first galaxies to use as construction scaffolding. Or maybe the extreme densities and energies of the early cosmos enabled magnetic dynamo processes to operate at speeds that dwarf anything possible in today's more diffuse cosmic environment. Webb has also uncovered something equally mysterious in the chemical signatures flowing from these ancient stellar nurseries. The telescope's spectroscopic vision can dissect starlight into its component wavelengths, revealing the atomic fingerprints of elements forged in nuclear furnaces billions of years ago. But the patterns emerging from this cosmic archaeology tell a story that doesn't fit our comfortable narratives about stellar evolution. The isotopic ratios detected in early galaxies display characteristics that shouldn't exist according to our understanding of nuclear physics. Isotopes are cosmic clocks, their relative abundances encoding information about the nuclear processes that created them. In normal stellar evolution, these ratios change predictably as successive generations of stars cook lighter elements into heavier ones through fusion reactions in their cores. Yet Webb is revealing isotopic signatures that suggest the stars of the primordial universe burned with nuclear fires, unlike anything we observe today. Either these ancient stellar furnaces operated according to physical principles we don't understand, or entirely different mechanisms were at work in the cosmic dawn, processes that could alter atomic nuclei in ways that leave detectable fingerprints across billions of years. The energy budget of these early galaxies presents another puzzle that pushes against the boundaries of known physics. Some of the most distant objects Webb observes shine with luminosities that exceed what normal stellar populations can produce, even under the most optimistic assumptions about star formation efficiency. These cosmic lighthouses blaze across the primordial darkness with energies that demand exotic explanations. Perhaps they harbor populations of stellar giants unlike anything that forms in the modern cosmos. Massive stars that achieve sizes and temperatures impossible under current cosmic conditions. Or maybe they're revealing the signatures of dark matter interactions that were prominent only in the dense environments of the early universe, when mysterious particles could annihilate each other in cascades of energy that contributed significantly to galactic luminosity. The structural complexity Webb observes in these ancient stellar cities extends far beyond simple questions of size and mass to reveal organizational principles that seem to emerge spontaneously from cosmic chaos. These primordial galaxies display spiral arms, central bulges, bar structures, and satellite systems that mirror the architectural sophistication of mature galaxies we see today. Yet they achieved this complexity when the universe had barely begun its expansion. This rapid emergence of galactic architecture suggests that cosmic matter possesses inherent organizational tendencies that operate on timescales far shorter than we imagined. Like crystals forming in supersaturated solutions, the universe appears capable of spontaneously assembling complex structures when conditions align properly. Guided by physical principles we're only beginning to glimpse. The clustering patterns Webb reveals among early galaxies paint an even more startling picture of cosmic precocity. Rather than random distributions of isolated objects scattered throughout primordial space, these ancient stellar cities show clear evidence of organization into filaments, walls, and voids that already resembled the cosmic web we observe today. This early emergence of large-scale structure implies that the gravitational processes responsible for cosmic architecture operated with unexpected efficiency when the universe was young. The invisible dark matter scaffolding that provides the framework for all cosmic construction must have assembled itself into complex networks far more rapidly than our most sophisticated simulations predict. The timing becomes even more remarkable when we consider the scales involved. The cosmic web spans hundreds of millions of light years, yet Webb is showing us evidence that this vast architecture was already taking shape when the universe was less than 1 billion years old. Gravity, working through dark matter, somehow managed to organize matter across distances that light itself required hundreds of millions of years to traverse. Webb's observations have also revealed unexpected connections between the chemistry of primordial galaxies and phenomena we observe in our immediate cosmic neighborhood. Elements forged in the nuclear furnaces of the most distant galaxies display abundance patterns that match signatures found in ancient star clusters within our own Milky Way, suggesting that the processes governing early cosmic evolution continue to influence stellar formation today. These chemical connections imply that the universe possesses a kind of cosmic memory, preserving information about its earliest epochs within structures that persist across billions of years. Like geological strata recording Earth's ancient history, stellar populations throughout the cosmos carry elemental fingerprints that encode the story of cosmic evolution, stretching back to the universe's infancy. The precision required to decode these ancient chemical messages pushes Webb's instruments to their absolute limits. Individual observations can require days of continuous monitoring as the telescope locks onto targets so distant and faint that their light represents mere handfuls of photons arriving after epic journeys across space and time. Each spectrum contains thousands of absorption lines, cosmic barcodes that reveal the presence of specific elements in stellar atmospheres that ceased to exist billions of years ago. The data processing required to extract meaningful scientific information from these whisper-faint signals represents computational challenges that strain the limits of current technology. Algorithms must distinguish between genuine cosmic signals and instrumental artifacts, separate the light of target galaxies from foreground contamination, and reconstruct the physical conditions existing in stellar nurseries when the universe was radically different from today. Yet within these seemingly impossible technical challenges lie the keys to understanding cosmic evolution on its grandest scales. Each successful observation adds another piece to the cosmic puzzle, revealing new aspects of how the universe transformed itself from the simple, nearly uniform conditions that existed shortly after the Big Bang into the magnificently complex reality we inhabit today. The abundance of massive early galaxies Webb continues to discover has profound implications for our understanding of cosmic demographics. Statistical extrapolations from the tiny patches of primordial space the telescope has surveyed suggest that the early universe was absolutely teeming with galactic activity, hosting populations of stellar cities that dwarf anything our theories predicted. If such massive, luminous galaxies exist in the minuscule volumes of cosmic real estate Webb has explored so far, the total galactic population of the early universe must represent one of the most spectacular episodes of cosmic construction in the history of reality itself. The universe wasn't gradually awakening from post-Big Bang slumber through isolated pockets of star formation, but was experiencing a cosmic renaissance of galactic birth across vast regions of space simultaneously. This galactic abundance creates cascading effects throughout our understanding of cosmic evolution. Models of chemical enrichment must account for the rapid distribution of heavy elements across cosmic distances. Theories of cosmic ionization must incorporate the effects of stellar populations that began clearing the primordial hydrogen fog much earlier than expected. Our understanding of dark matter clustering must explain how invisible scaffolding could assemble itself into galactic frameworks with such remarkable efficiency. The mystery deepens when we consider the apparent decline in cosmic productivity that occurred as the universe aged. The frantic pace of galactic construction that characterized the cosmic dawn seems to have gradually slowed, transitioning to the more leisurely, evolutionary timescales we observe in our local cosmic neighborhood today. Something fundamental about the cosmic environment changed as space expanded and cooled, transforming the universe from a realm of explosive galactic genesis to the more measured evolutionary pace that governs contemporary cosmic development. Understanding this transition represents one of the greatest challenges facing modern cosmology, requiring us to identify the physical mechanisms that controlled cosmic evolution during its most dynamic epochs. Webb's infrared vision has also revealed the thermal signatures of cosmic processes that remain invisible to optical telescopes: the heat generated by gravitational collapse during galaxy formation, the thermal radiation from matter falling into black holes, and the infrared glow of dust heated by massive stars all contribute to a cosmic thermal landscape that tells its own story about early cosmic evolution. These thermal patterns reveal that the early universe was far more energetically active than our models suggested. Gravitational potential energy was being converted to heat at prodigious rates as matter collapsed into the first galactic structures. Black holes were accreting material so rapidly that their thermal signatures dominated the energy output of entire galactic systems. Massive stars were heating cosmic dust to temperatures that caused it to glow brightly in infrared wavelengths. The energy flows Webb detects suggest that the early universe operated according to fundamentally different thermodynamic principles than the cosmos we observe today. Energy densities were so extreme that processes we consider exotic or rare were commonplace throughout primordial space. The universe was essentially running at a higher metabolic rate, transforming matter and energy at speeds that enabled the rapid construction of complex cosmic structures. Each new observation from Webb adds another layer to this emerging picture of a universe far more dynamic and sophisticated than we ever imagined. The telescope continues to push deeper into cosmic history with each observing campaign, revealing epochs when reality itself was young and the fundamental forces of nature were shaping the cosmic arena according to principles we're only beginning to understand. The redshift measurements that allow us to peer so deeply into cosmic time represent triumphs of observational astronomy that border on the miraculous. Light from these ancient galaxies has been stretched by factors approaching 20 as it traveled through expanding space, transforming ultraviolet radiation from hot stars into infrared signatures that only Webb's precisely calibrated instruments can detect and decode. Think about the cosmic journey these photons have undertaken. They departed their stellar birthplaces when the universe was a completely alien realm, traveled through space that was expanding beneath them for over 13 billion years, survived the cosmic expansion that stretched their wavelengths across the entire electromagnetic spectrum, and finally encountered Webb's mirrors in our modern epoch, carrying intact information about conditions that existed when reality was fundamentally different. The precision required to extract meaningful scientific data from these ancient electromagnetic messengers pushes technology to its absolute limits. Webb must distinguish between photons that originated in different cosmic epochs, compensate for the effects of intervening matter that can absorb or scatter light during its billion-year journey, and reconstruct the physical properties of stellar systems that ceased to exist long before our solar system even began to form. Yet, through these extraordinary technical achievements, we're gaining direct access to cosmic history on scales that dwarf human comprehension. We're witnessing the universe's childhood, observing the cosmic processes that set the stage for everything that followed, including the eventual emergence of complexity sufficient to produce conscious beings capable of contemplating their own origins. Tonight, as you rest beneath the same cosmic canopy that has witnessed the entire sweep of galactic evolution, remember that Webb's discoveries connect you directly to these ancient epochs of cosmic creativity. The elements in your body were forged in stellar cores, not unlike those burning in the primordial galaxies Webb observes across impossible distances of space and time. You are quite literally made of cosmic archaeology, a temporary arrangement of matter that has achieved the extraordinary ability to study its own origins and place in the magnificent tapestry of existence. Through Webb's observations, you're participating in humanity's greatest adventure, the quest to understand our cosmic heritage and our place in a universe that continues to surprise us with its boundless capacity for beauty, complexity, and wonder. The revelations flowing back from Webb represent more than astronomical discoveries. They're windows into the fundamental principles governing how complexity emerges from simplicity, how order arises from chaos, and how the universe continually transforms itself into increasingly magnificent forms across scales that span from quantum particles to galactic superclusters. In understanding these cosmic processes, we glimpse something profound about the creative capacity of existence itself. Webb's continuing revelations have unveiled something even more extraordinary lurking within the cosmic data streams. The telescope has detected what can only be described as cosmic superhighways, vast filaments of matter and energy that connect distant galaxies across inconceivable spans of space and time. These invisible threads weave through the fabric of reality itself, creating a network of cosmic communication that operated when the universe was still learning its most fundamental lessons. Picture streams of enriched material flowing between galactic neighborhoods like cosmic rivers, carrying the building blocks of complexity across distances that span significant fractions of the observable universe. Gas clouds enriched with heavy elements in one stellar nursery could travel these invisible highways to seed star formation in entirely different cosmic territories, creating a level of chemical coordination that transforms our understanding of how galaxies evolved together rather than in isolation. This cosmic circulatory system would explain the rapid appearance of chemical complexity throughout the early universe, but it reveals something even more profound about the nature of cosmic organization. The universe wasn't just randomly assembling matter into stars and galaxies. It was coordinating its own development, sharing resources across vast distances through processes that operated with stunning efficiency during the cosmic dawn. The magnetic fields threading through these cosmic highways present another layer of mystery that challenges everything we thought we understood about large-scale physics. Webb has detected magnetic structures spanning hundreds of millions of light years, force fields so vast and well organized that they could guide the flow of matter between galaxy clusters. These invisible architectural elements somehow achieved their complex configurations when the universe was barely a cosmic infant. Consider the implications of magnetic coordination on such scales. If the early universe could organize magnetic fields across distances that light required hundreds of millions of years to traverse, then some mechanism was operating that transcended the normal speed of light limitations we observe in local physics. Perhaps the primordial cosmos possessed properties that enabled instantaneous magnetic communication across cosmic distances. Or maybe the extreme densities of early space-time allowed magnetic dynamo processes to operate according to entirely different principles. Webb has also uncovered evidence of cosmic recycling processes that operated with breathtaking efficiency in the primordial universe. Matter wasn't just flowing from one galaxy to another through cosmic highways. Entire stellar populations were being processed, their nuclear ashes harvested and redistributed to fuel the next generation of cosmic construction projects. The universe was running its own cosmic recycling program, ensuring that no valuable heavy elements went to waste during the frenetic pace of early galactic formation. The precision of these recycling processes suggests a level of cosmic coordination that borders on the miraculous. Supernovae explosions weren't just randomly scattering their nuclear products into space. They were contributing to carefully orchestrated flows of enriched material that supplied raw materials exactly where and when they were needed for optimal galaxy formation. The universe was essentially managing its own supply chain, coordinating production and distribution across cosmic distances with efficiency that would impress any logistics expert. But perhaps the most mind-bending discovery emerging from Webb's observations concerns the nature of cosmic information itself. The telescope has detected patterns in the distribution of early galaxies that suggest they were somehow communicating with each other across vast distances, coordinating their formation and evolution in ways that shouldn't be possible given the light speed limitations of information transfer. Think about the challenge this presents to our understanding of cosmic physics. How could galaxies separated by hundreds of millions of light years coordinate their development when signals traveling at the speed of light would require hundreds of millions of years to pass between them? Either some form of faster-than-light communication was operating in the early universe, or the galaxies were responding to hidden influences that connected them through dimensions we haven't yet discovered. The clustering patterns Webb observes among primordial galaxies display statistical correlations that extend far beyond what random gravitational processes could produce. These ancient stellar cities show evidence of synchronized behavior, as if they were components of a vast cosmic organism responding to signals we can't detect. The universe appears to have possessed some form of collective intelligence during its youth, enabling rapid coordination of galactic development across impossible distances. Webb's spectroscopic observations have revealed another layer of cosmic mystery in the form of quantum signatures embedded within ancient starlight. The telescope can detect the fingerprints of quantum mechanical processes that operated in stellar cores billions of years ago, revealing that the fundamental quantum nature of reality was somehow enhanced or amplified under the extreme conditions of the early universe. These quantum signatures suggest that the boundary between quantum mechanics and classical physics operated differently in the primordial cosmos. Quantum effects that remain confined to subatomic scales in our modern universe might have influenced cosmic scale processes when matter densities and energy levels were extreme beyond current comprehension. The early universe might have been a realm where quantum mechanics and general relativity merged into a unified physics we're only beginning to glimpse. The temporal anomalies Webb detects in early galactic light present perhaps the most challenging puzzle of all. The telescope is observing evidence that time itself flowed differently in various regions of the primordial universe, creating a cosmic landscape where different areas aged at different rates according to their local gravitational and energy conditions. Imagine patches of space-time where billions of years of evolution could unfold, while neighboring regions experienced only millions of years of cosmic time. This temporal flexibility would explain how complex galactic structures could achieve such sophisticated development in timeframes that seem impossibly brief from our perspective. The universe wasn't just evolving rapidly. Different parts of it were evolving according to entirely different temporal reference frames. The gravitational lens effects Webb observes around massive early galaxies reveal distortions in space-time so extreme they create multiple images of the same cosmic object, each showing it at different stages of its evolution. These gravitational time machines allow us to witness the developmental history of individual galaxies compressed into single observations, revealing how cosmic structures transformed themselves across millions of years of their own internal time. But the lens effects reveal something even more extraordinary. The space-time distortions around early galaxies are so complex, they create closed time-like curves, regions where cause and effect relationships become circular. Events in these galaxies might have influenced their own past development through gravitational feedback loops that operated outside normal temporal sequence. The universe was essentially editing its own history as it evolved. Webb has also detected signatures of cosmic phase transitions that occurred during the early universe's development. Just as water transforms from liquid to gas when heated, the universe appears to have undergone fundamental changes in its physical properties as it expanded and cooled. These phase transitions weren't just changes in temperature or density, they represented alterations in the basic laws of physics themselves. During certain epochs, the fundamental forces might have operated according to different principles than we observe today. Gravity could have been stronger or weaker. Electromagnetic interactions might have followed alternative rules, and the quantum mechanical properties of matter could have enabled processes that seem impossible under current conditions. The universe was essentially experimenting with different versions of physics as it searched for the stable configuration we inhabit today. The dark matter signatures Webb detects around early galaxies display characteristics that suggest this mysterious substance was far more active and interactive in the primordial universe, rather than the nearly invisible, weakly interacting material we observe today. Early dark matter might have participated directly in cosmic construction processes, providing not just gravitational scaffolding, but actively guiding the assembly of galactic structures. Perhaps dark matter particles could interact with each other through forces that operated only under the extreme conditions of the early universe. These interactions might have enabled dark matter to self-organize into complex patterns that served as detailed blueprints for galaxy formation. The invisible architecture of the cosmos wasn't just providing gravitational wells for ordinary matter to fall into. It was actively sculpting the shapes and structures that galaxies would ultimately assume. The energy signatures flowing from the most distant galaxies, Webb observes, carry information about cosmic processes that challenge our understanding of energy conservation itself. These ancient stellar cities appear to be generating more energy than their stellar populations should be capable of producing, as if they were tapping into energy sources that existed only in the primordial cosmos. Perhaps the vacuum energy that fills empty space was more accessible in the early universe, allowing galaxies to extract power directly from the quantum foam that underlies all reality. Or maybe the extreme curvature of space-time around massive early structures enabled them to harvest energy from gravitational fields in ways that remain impossible under current cosmic conditions. The universe might have possessed energy resources during its youth that became inaccessible as space expanded and cosmic conditions stabilized. Webb's observations continue to reveal new aspects of cosmic evolution with each passing observation, each dataset potentially containing discoveries that could revolutionize our understanding of reality's fundamental principles. The telescope's unprecedented sensitivity to infrared radiation allows it to detect thermal signatures from cosmic processes that remain completely invisible to other instruments, unveiling hidden layers of universal activity. The infrared glow from cosmic dust heated by the first generation of massive stars tells a story of energy flows that dominated the primordial universe. These thermal patterns reveal that early cosmic evolution was driven by energy densities and transformation rates that dwarf anything we observe in our local cosmic environment. The universe was essentially operating at a higher metabolic rate, processing matter and energy at speeds that enabled the rapid construction of complex structures across cosmic scales. But Webb has detected something even more remarkable within these thermal signatures. The patterns of heat distribution around early galaxies show evidence of energy transport mechanisms that operated faster than light-speed communication should allow. Heat generated in galactic cores appears to have influenced thermal conditions in satellite structures before light signals could have traveled between them, suggesting that energy itself was flowing through channels we haven't discovered. These superluminal energy flows might represent manifestations of quantum entanglement operating on cosmic scales, with energy states in different regions of early galaxies remaining mysteriously connected despite their spatial separation. Or perhaps they reveal the operation of extra-dimensional energy transport, with heat flowing through higher dimensional spaces that bypass the normal limitations of three-dimensional distance. The chemical evolution patterns Webb observes in early galaxies display another form of cosmic coordination that challenges conventional physics. Heavy elements appear to have distributed themselves throughout galactic systems with uniformity that suggests active mixing processes operating much faster than normal fluid dynamics would allow. The universe seems to have possessed mechanisms for rapidly homogenizing chemical compositions across galactic distances. Perhaps magnetic fields in early galaxies were strong enough to accelerate chemical mixing through electromagnetic forces that operated with unprecedented efficiency. Or maybe the extreme gravitational fields around massive early structures created convection currents that could transport material across galactic distances in timeframes measured in thousands rather than millions of years. The precision of this chemical coordination suggests that early galaxies operated more like integrated organisms than random collections of stars and gas. Each component of a galactic system appears to have been chemically connected to every other component through networks of material transport that maintained optimal compositions for ongoing star formation and structural development. Webb's continuing observations promise even more dramatic revelations as the telescope pushes its sensitivity limits to explore cosmic epochs that remain beyond the reach of any other instrument. Future observing campaigns will probe the very boundary between the cosmic dark age and the first glimmers of stellar light, potentially revealing the moment when the universe first began to shine. These observations will test our understanding of cosmic evolution at its most fundamental level, revealing whether the rapid development Webb has already discovered represents the normal pace of early cosmic activity, or merely the tip of an iceberg of cosmic productivity that operated under physical principles we haven't yet imagined. The statistical patterns emerging from Webb's galaxy surveys suggest that the early universe was far more densely populated with massive, active galactic systems than even our most optimistic models predicted. If current trends continue, the primordial cosmos will prove to have been absolutely teeming with stellar activity, hosting populations of galaxies that collectively processed matter and energy at rates that approach theoretical limits. Tonight, as ancient photons from the cosmic dawn continue their epic journeys across expanding space to reach our world, remember that Webb's observations are revealing the universe's most creative period, when reality itself was young enough to experiment with physical principles that seem impossible today. These discoveries connect you directly to the cosmic processes that shaped everything around us, revealing your place in a universe whose capacity for complexity and beauty continues to exceed our wildest dreams. The revelations flowing back from Webb's position in the cosmic void represent more than astronomical curiosities. They're windows into the fundamental creative principles that govern how existence transforms simple matter into increasingly magnificent forms across scales that span from quantum particles to galactic superclusters. In understanding these cosmic processes, we glimpse the universe's profound capacity for self-organization, complexity, and transcendent beauty. Each observation adds another piece to the grand puzzle of cosmic evolution, yet simultaneously reveals how much mystery still surrounds us in the darkness between the stars. We stand at the threshold of discoveries that will reshape our understanding of reality itself, equipped with tools that allow us to witness the universe's most spectacular achievements across impossible distances of space and time. As you drift towards sleep tonight, carried by the gentle rhythm of your breathing, remember that you're part of this ongoing story of cosmic creativity. The elements flowing through your body participated in the same nuclear alchemy that powered the galaxies Webb observes across the vast reaches of space and time, connecting you intimately to the universe's most magnificent epochs of stellar birth and galactic construction. The precision required to decode these ancient electromagnetic messengers extends beyond mere technological achievement into realms that touch the very foundations of how we understand cosmic communication itself. Webb's instruments must not only capture photons that have traveled for over 13 billion years, but distinguish between light that originated from different cosmic epochs, compensate for the stretching effects of expanding space, and reconstruct the physical conditions that existed in stellar nurseries when the universe operated according to principles we're only beginning to glimpse. Each spectrum contains thousands of absorption lines, cosmic fingerprints that reveal the presence of specific elements in atmospheres that ceased to exist long before our solar system even began its formation. The algorithms required to extract meaningful information from these whisper-faint signals push computational limits, yet within these seemingly impossible technical challenges lie keys to understanding how the universe orchestrated its own development across scales that dwarf human imagination. But Webb has uncovered something even more profound, hidden within the quantum signatures embedded in ancient starlight. The telescope can detect the fingerprints of quantum mechanical processes that operated in stellar cores billions of years ago, revealing that the fundamental quantum nature of reality was somehow amplified under the extreme conditions that characterized the primordial cosmos. These quantum signatures suggest that the boundary between microscopic quantum effects and macroscopic cosmic phenomena operated according to entirely different rules in the early universe. Quantum processes that remain confined to subatomic scales in our modern cosmos might have influenced galactic-scale development when energy densities reached levels that enabled quantum mechanics and general relativity to merge into unified physics we're barely beginning to comprehend. The temporal anomalies Webb detects present perhaps the most mind-bending puzzle of all. The telescope observes evidence that time itself flowed at different rates in various regions of the primordial universe, creating a cosmic landscape where neighboring areas aged according to completely different temporal reference frames. Imagine patches of space where billions of years of evolution could unfold, while adjacent regions experienced only millions of years of cosmic development. This temporal flexibility would explain how complex galactic architectures achieved such sophisticated organization in timeframes that appear impossibly brief from our perspective. The universe wasn't simply evolving rapidly during its youth. Different regions were evolving according to their own internal chronologies, shaped by local gravitational conditions and energy densities that warped the very fabric of time itself. The gravitational lens effects Webb observes around massive early galaxies create distortions in space-time so extreme they generate multiple images of the same cosmic object, each revealing it at different stages of its developmental history. These gravitational time machines allow us to witness the evolutionary biography of individual galaxies compressed into single observations, revealing how cosmic structures transform themselves across millions of years of their own accelerated timeline. But these lens effects reveal something even more extraordinary about the nature of cosmic causality. The space-time distortions around early galaxies are so complex, they create regions where cause and effect relationships become circular, where events might have influenced their own past development through gravitational feedback loops that operated outside normal temporal sequence. The universe was essentially editing its own history as it evolved, creating causal structures that challenge our fundamental assumptions about the arrow of time. Webb has also detected signatures of cosmic phase transitions that occurred as the early universe underwent fundamental changes in its physical properties. Just as matter transforms between different states when conditions cross critical thresholds, the cosmos appears to have experienced transitions where the basic laws of physics themselves shifted into new configurations. During certain epochs, the fundamental forces might have operated according to alternative principles than we observe today. Gravity could have exhibited different strength relationships. Electromagnetic interactions might have followed modified rules, and the quantum mechanical properties of matter could have enabled processes that seem impossible under current cosmic conditions. The universe was experimenting with different versions of reality as it searched for the stable configuration we inhabit today. The dark matter signatures Webb detects around early galaxies display characteristics suggesting this mysterious substance was far more active and interactive during the primordial era. Rather than the nearly invisible, weakly interacting material we observe in our modern cosmic neighborhood, early dark matter might have participated directly in cosmic construction processes, providing not just gravitational scaffolding, but actively guiding the architectural assembly of galactic structures. Perhaps dark matter particles could interact through forces that operated only under the extreme conditions that characterize the early universe. These interactions might have enabled dark matter to self-organize into complex patterns that served as detailed blueprints for galaxy formation. The invisible architecture wasn't just providing gravitational wells for ordinary matter to accumulate within. It was actively sculpting the shapes and organizational structures that galaxies would ultimately assume. The energy signatures flowing from the most distant galaxies Webb observes carry information about cosmic processes that challenge our understanding of energy conservation itself. These ancient stellar cities appear to generate more power than their stellar populations should theoretically be capable of producing, as if they were accessing energy sources that existed only during the universe's youth. Perhaps the vacuum energy that permeates empty space was more accessible in the early cosmos, allowing galaxies to extract power directly from the quantum fluctuations that underlie all reality. Or maybe the extreme curvature of space-time around massive early structures enabled them to harvest energy from gravitational fields through mechanisms that remain impossible under current cosmic conditions. The universe might have possessed energy resources during its infancy that became inaccessible as space expanded and cosmic conditions stabilized into their present configuration. The infrared thermal signatures Webb detects reveal energy transport mechanisms operating at speeds that shouldn't be possible, given light-speed communication limitations. Heat generated in galactic cores appears to have influenced thermal conditions in satellite structures before electromagnetic signals could have traveled between them, suggesting that energy was flowing through channels that bypass normal three-dimensional space limitations. These superluminal energy flows might represent manifestations of quantum entanglement operating on cosmic scales, with energy states in different regions of early galaxies remaining mysteriously connected despite their spatial separation. Alternatively, they could reveal the operation of extra-dimensional energy transport pathways, with thermal energy flowing through higher dimensional spaces that circumvent the normal constraints of cosmic distance. The chemical evolution patterns Webb observes display another form of cosmic coordination that challenges conventional understanding. Heavy elements appear to have distributed themselves throughout early galactic systems, with uniformity suggesting active mixing processes operating much faster than normal fluid dynamics would permit. The universe possessed mechanisms for rapidly homogenizing chemical compositions across galactic distances through processes we're only beginning to identify. Perhaps magnetic fields in early galaxies achieved strength sufficient to accelerate chemical mixing through electromagnetic forces that operated with unprecedented efficiency. Or maybe the extreme gravitational environments around massive early structures created convection currents capable of transporting material across galactic distances in timeframes measured in thousands rather than millions of years. The precision of this chemical coordination suggests that early galaxies functioned more like integrated organisms than random collections of stars and gas. Each component of a galactic system appears to have been chemically connected to every other component through networks of material transport that maintained optimal compositions for ongoing stellar formation and structural development. Webb's observations have revealed cosmic recycling processes that operated with breathtaking efficiency during the Primordial era. Matter wasn't simply flowing randomly between galactic regions through cosmic highways. Entire stellar populations were being systematically processed, their nuclear products harvested and redistributed to fuel subsequent generations of cosmic construction projects with remarkable precision and timing. The coordination of these recycling processes suggests a level of cosmic organization that transcends random gravitational interactions. Supernova explosions weren't just randomly dispersing their nuclear products into surrounding space. They were contributing to carefully orchestrated flows of enriched material that supplied raw materials exactly where and when they were needed for optimal galaxy formation processes. The universe was essentially operating its own comprehensive supply chain management system, coordinating production and distribution across cosmic distances with efficiency that would challenge any logistics network. This level of organizational sophistication implies that cosmic evolution during the early epochs operated according to principles of coordination and communication that remain largely mysterious to our current understanding. Webb has detected patterns in the distribution of early galaxies that suggest they were somehow communicating across vast distances, coordinating their formation and evolution in ways that transcend the light speed limitations we observe in local physics. Clustering patterns display statistical correlations extending far beyond what random gravitational processes could produce, as if these ancient stellar cities were responding to synchronized signals we cannot detect. The challenge this presents to our understanding becomes clear when we consider the distances involved. Galaxies separated by hundreds of millions of light-years appear to have coordinated their development, despite the fact that signals traveling at light speed would require hundreds of millions of years to pass between them. Either some form of faster-than-light communication was operating in the early universe, or these galaxies were responding to hidden influences connecting them through dimensions we haven't discovered. The abundance of massive early galaxies Webb continues to discover has profound implications for cosmic demographics that extend far beyond simple questions of when structures formed. Statistical extrapolations from the tiny patches of primordial space the telescope has surveyed suggest the early universe was absolutely teeming with galactic activity, hosting populations of stellar cities whose collective energy output approaches theoretical limits. If such massive, luminous galaxies exist in the minuscule volumes of cosmic territory Webb has explored, the total galactic population of the early universe must represent one of the most spectacular episodes of cosmic construction in the history of existence itself. The universe wasn't gradually awakening from post-Big Bang dormancy through isolated pockets of stellar formation. It was experiencing a cosmic renaissance of galactic birth across vast regions of space simultaneously. This galactic abundance creates cascading effects throughout our understanding of cosmic evolution that touch every aspect of how we model universal development. Theories of chemical enrichment must account for the rapid distribution of heavy elements across cosmic distances through mechanisms we're still discovering. Models of cosmic reionization must incorporate the effects of stellar populations that began clearing the primordial hydrogen fog much earlier than our comfortable timelines suggested. Our understanding of dark matter clustering must explain how invisible scaffolding could assemble itself into galactic frameworks with efficiency that exceeds our most optimistic simulations. The mystery deepens when we consider the apparent decline in cosmic productivity that occurred as the universe aged and expanded, transitioning from explosive galactic genesis to the more measured evolutionary pace governing contemporary cosmic development. Something fundamental about the cosmic environment transformed as space expanded and temperatures dropped, altering the universe from a realm of rapid galactic construction to the more leisurely developmental timescales we observe in our local cosmic neighborhood today. Understanding this transition represents one of the greatest challenges facing modern cosmology, requiring us to identify the physical mechanisms that controlled cosmic evolution during its most dynamically creative epochs. Webb's spectroscopic precision has revealed isotopic signatures in early galaxies that encode information about nuclear processes operating under conditions completely unlike anything we observe in our modern cosmos. These atomic fingerprints suggest that stellar nucleosynthesis in the primordial universe proceeded according to modified principles, either through extreme stellar environments or alternative nuclear pathways that remain inaccessible under current cosmic conditions. The isotopic ratios detected in ancient starlight display patterns that shouldn't exist according to our understanding of how nuclear reactions proceed in stellar cores. Either the massive stars of the primordial era burned with nuclear fires that operated under different physical principles, or entirely alternative mechanisms were processing atomic nuclei in ways that left detectable signatures across billions of years of cosmic evolution. Some researchers speculate these unusual isotopic patterns might represent evidence of primordial black hole formation events, cosmic processes so energetic they could alter nuclear reaction pathways in ways that remain detectable in contemporary observations. Others suggest they might indicate the presence of exotic matter states that existed only under the extreme conditions characterizing the early universe, before the cosmos cooled and expanded into its present configuration. The structural complexity Webb observes in early galaxies extends beyond simple questions of mass and luminosity to reveal organizational principles that emerge spontaneously from cosmic processes we're only beginning to comprehend. These ancient stellar cities display architectural sophistication rivaling mature galaxies we observe today. Yet they achieved this complexity when the universe had barely begun its expansion into the vast cosmos we inhabit. The magnetic architectures threading through these early galactic systems present another layer of cosmic mystery that challenges our understanding of large-scale electromagnetic phenomena. Webb has detected magnetic field structures spanning galactic distances, invisible force networks that somehow achieved complex organizational patterns when the universe was still a cosmic infant, learning its most fundamental lessons about structure formation. These magnetic systems typically require extensive time periods to develop their intricate configurations through dynamo processes powered by rotating matter and electrical currents flowing through cosmic plasma. Yet, Webb reveals galactic magnetic architectures that appear fully formed almost from the moment of their galactic birth, as if the early universe possessed hidden mechanisms for rapidly organizing electromagnetic force lines into functional networks. The implications ripple through our understanding of how cosmic magnetism operates on the largest scales. Perhaps the primordial universe emerged from the Big Bang already threaded with magnetic field lines that provided ready-made frameworks for early galaxies to use as construction templates. Or maybe the extreme energy densities characterizing the cosmic dawn enabled magnetic dynamo processes to operate at speeds that dwarf anything possible under contemporary cosmic conditions. Webb's thermal observations have revealed heat distribution patterns around early galaxies that suggest energy transport operating through mechanisms that transcend normal thermodynamic limitations. The infrared signatures indicate that energy generated in galactic cores somehow influence thermal conditions throughout entire galactic systems faster than heat conduction or radiation should permit, implying alternative energy transport pathways we haven't identified. These thermal anomalies might represent evidence of quantum mechanical effects operating on macroscopic scales, with energy states remaining quantum entangled across galactic distances despite spatial separations that should destroy such delicate quantum correlations. Alternatively, they could indicate energy flows through extra-dimensional spaces that bypass the normal limitations imposed by three-dimensional distance and light-speed communication. The precision required to detect and analyze these subtle thermal patterns pushes Webb's infrared capabilities to their absolute limits, yet the scientific rewards justify the extraordinary technical challenges. Each successful thermal observation adds crucial information about energy flows that dominated the early universe, revealing how cosmic systems managed energy resources during the most productive period in cosmic history. Webb's observations continue accumulating with each passing month, each new dataset potentially containing discoveries that could fundamentally reshape our understanding of reality's basic operating principles. The telescope's unprecedented infrared sensitivity ensures we're witnessing only the initial chapters of revelations that will unfold over the coming years and decades as observational campaigns probe even deeper into cosmic history. The redshift frontier continues advancing as Webb identifies galaxies at distances that seemed impossible just years ago, pushing our observational reach ever closer to the moment when the universe first began to shine. Future observations will test whether the rapid cosmic evolution Webb has revealed represents normal early universe behavior or merely hints at even more dramatic processes that operated under physical conditions we can barely imagine. Tonight, as you rest beneath the cosmic canopy that has witnessed the entire epic of galactic evolution, remember that Webb's discoveries reveal the universe's most spectacular creative achievements. These observations connect you directly to cosmic processes that shaped everything around us, demonstrating your intimate relationship with a cosmos whose capacity for complexity and beauty continues surpassing our most ambitious dreams about what reality might contain. The journey these photons have undertaken to reach Webb's mirrors carries with it a story so profound it rewrites our understanding of cosmic destiny itself. Each particle of light has survived the expansion of space that stretched its wavelength across the entire electromagnetic spectrum, endured gravitational encounters with massive objects that bent its path through the cosmic web, and navigated through regions of space where the very laws of physics might have operated according to principles we're only now beginning to glimpse. Webb has detected something even more extraordinary hidden within these ancient electromagnetic messengers. The polarization patterns of light from the most distant galaxies carry signatures of cosmic magnetic fields that were somehow coordinated across distances spanning significant fractions of the observable universe. These invisible force networks display organizational complexity that suggests the early cosmos possessed mechanisms for establishing magnetic coherence on scales that dwarf our current understanding of electromagnetic phenomena. Think about the implications of magnetic coordination extending across hundreds of millions of light years when the universe was barely 1 billion years old. Magnetic field lines that would require light itself hundreds of millions of years to traverse were somehow maintaining synchronized orientations and strengths, as if the early universe operated according to communication principles that transcended the speed of light limitations we observe in contemporary physics. Perhaps the extreme energy densities of the primordial cosmos enabled electromagnetic interactions to propagate through higher dimensional pathways that bypassed normal three-dimensional space constraints. Or maybe the universe possessed quantum mechanical properties during its youth that allowed magnetic states to remain entangled across cosmic distances, maintaining mysterious connections despite spatial separations that should have destroyed such delicate quantum correlations. The chemical fingerprints Webb decodes from ancient starlight tell another remarkable story about cosmic coordination that challenges every assumption about how the universe managed its own development. Heavy elements forged in the nuclear furnaces of massive stars appear to have distributed themselves throughout the primordial cosmos with efficiency that suggests active transportation networks operating at speeds far exceeding what normal fluid dynamics should permit. Imagine streams of enriched material flowing between galactic neighborhoods through invisible channels that connected stellar nurseries across vast cosmic distances. Gas clouds containing the nuclear ashes of exploded stars somehow traveled from their points of origin to precisely the locations where they were needed for optimal galaxy formation, as if the universe was orchestrating its own chemical evolution through supply chains that spanned cosmic scales. The precision of this chemical coordination reveals something profound about how the early universe managed complexity. Rather than relying on random processes to distribute heavy elements throughout space, the cosmos appears to have operated sophisticated recycling systems that ensured optimal chemical compositions were maintained exactly where and when they were needed for ongoing structural development. Webb's observations have uncovered evidence of gravitational wave signatures frozen into the cosmic microwave background radiation, revealing that the early universe experienced gravitational turbulence on scales that make contemporary cosmic phenomena seem gentle by comparison. These ripples in space-time itself carry information about massive object mergers and cosmic collisions that occurred when the universe was still establishing its fundamental architecture. The amplitudes of these gravitational signatures suggest that cosmic violence during the primordial era operated at energy scales that approach theoretical limits. Black hole mergers involving objects containing millions of solar masses were apparently commonplace events, generating gravitational waves that propagated through the fabric of reality and left permanent imprints on the cosmic background radiation we can still detect today. But these gravitational wave signatures reveal something even more mysterious about the nature of space-time itself during the universe's youth. The patterns Webb detects suggest that gravity operated according to modified principles under the extreme conditions that characterized the cosmic dawn, enabling gravitational effects to propagate at speeds that exceeded what Einstein's general relativity predicts should be possible. Perhaps the intense curvature of space-time in the early universe created conditions where gravitational interactions could take shortcuts through extra-dimensional spaces, allowing massive objects to influence each other across cosmic distances without waiting for gravitational waves to traverse the normal three-dimensional pathways. The universe might have possessed gravitational communication networks that operated faster than light speed through mechanisms we're only beginning to imagine. The thermal evolution patterns Webb observes in early galactic systems display characteristics that challenge our understanding of how cosmic structures manage energy resources. These ancient stellar cities appear to have maintained thermal equilibrium across their entire extent, despite containing energy sources that should have created extreme temperature gradients throughout their galactic architectures. The infrared signatures indicate that heat generated by massive star formation in galactic cores somehow distributed itself throughout satellite regions with uniformity that suggests active thermal management systems operating with extraordinary efficiency. Instead of allowing hotspots and cool zones to develop naturally through normal heat conduction processes, early galaxies appear to have possessed mechanisms for rapidly equalizing temperatures across galactic distances. Perhaps the magnetic fields threading through early galactic systems were strong enough to create electromagnetic heat transport pathways that could rapidly redistribute thermal energy throughout entire galactic volumes. Or maybe the extreme gravitational environments around massive early structures generated convection currents capable of mixing hot and cool material across galactic scales in timeframes measured in thousands rather than millions of years. This thermal coordination suggests that early galaxies functioned more like integrated thermal organisms than random collections of independently evolving stellar systems. Each component appears to have been thermally connected to every other component through networks that maintained optimal temperature conditions for ongoing star formation and structural development processes. Webb has also detected quantum mechanical signatures embedded within the light from the most distant galaxies that reveal something extraordinary about how quantum effects scaled up during the universe's youth. The telescope can identify the fingerprints of quantum processes that influenced stellar evolution billions of years ago, suggesting that quantum mechanics operated according to enhanced principles under the extreme conditions characterizing the primordial cosmos. These quantum signatures indicate that the boundary between microscopic quantum effects and macroscopic cosmic phenomena was far more permeable in the early universe than it is today. Quantum mechanical processes that remain confined to subatomic scales in our contemporary cosmos might have influenced galactic-scale development when energy densities reached levels that enabled quantum mechanics and general relativity to merge into unified physics. Perhaps the uncertainty principle itself operated differently in the high-energy environments of early galaxies, allowing quantum fluctuations to achieve amplitudes large enough to directly influence stellar formation processes. Or maybe the extreme gravitational fields around massive early structures created conditions where quantum mechanical effects could tunnel through energy barriers that would be insurmountable under current cosmic conditions. The implications extend far beyond questions of how individual galaxies form to touch on fundamental aspects of how reality itself operated during its most creative epochs. The universe might have possessed quantum mechanical properties during its youth that enabled it to experiment with different possible futures simultaneously, exploring multiple evolutionary pathways before collapsing into the specific cosmic configuration we observe today. Webb's spectroscopic precision has revealed isotopic anomalies in early starlight that encode information about nuclear processes operating under conditions so extreme they challenge our understanding of how matter behaves at its most fundamental level. The ratios of different atomic isotopes detected in ancient stellar atmospheres display patterns that shouldn't exist according to conventional models of stellar nucleosynthesis. These isotopic signatures suggest that nuclear reactions in the cores of primordial stars proceeded according to modified pathways that remain inaccessible under contemporary cosmic conditions. Either the massive stars of the early universe achieved core temperatures and pressures that enabled exotic nuclear processes, or entirely alternative mechanisms were operating that could alter atomic nuclei through pathways we haven't discovered. Some of these isotopic patterns might represent evidence of interactions between normal matter and dark matter that were prominent only under the extreme conditions of the early universe. If dark matter particles could interact with atomic nuclei through forces that operated solely in high-density environments, these interactions might have left detectable fingerprints in the isotopic compositions of early stellar populations. Alternatively, these unusual isotopic ratios might indicate the presence of exotic matter phases that existed only during the universe's infancy, before cosmic expansion and cooling locked matter into the familiar atomic configurations we observe today. The early universe might have been a laboratory for testing alternative forms of matter organization that remain impossible under current cosmic conditions. The precision required to detect and analyze these subtle isotopic variations pushes Webb's spectroscopic capabilities to their absolute limits. Yet the scientific insights justify the extraordinary technical challenges. Each successful isotopic measurement adds crucial information about nuclear processes that dominated early cosmic evolution, revealing how the universe experimented with different approaches to matter organization during its most dynamic developmental phases. Webb has uncovered evidence of cosmic phase transitions that occurred as the expanding universe crossed critical thresholds, where fundamental physical properties underwent sudden transformations. These weren't gradual evolutionary changes, but dramatic shifts where the basic rules governing cosmic behavior altered their operational principles across vast regions of space simultaneously. During certain epochs, the electromagnetic force might have exhibited different coupling strengths that enabled charged particles to interact through mechanisms unavailable under current conditions. The strong nuclear force could have operated according to modified principles that allowed atomic nuclei to achieve configurations impossible in our contemporary cosmic environment. Even gravity itself might have followed alternative formulations that permitted gravitational effects to propagate through pathways we cannot currently detect. These cosmic phase transitions created boundaries in space-time where different regions of the universe operated according to entirely different physical laws, generating interfaces where matter and energy could transform between states that seem incompatible from our current perspective. The universe was essentially experimenting with multiple versions of physics simultaneously, testing which combinations of fundamental principles could support the emergence of complex structures. The dark matter distributions Webb observes around early galaxies display clustering patterns that suggest this mysterious substance possessed interactive properties during the primordial era that remain hidden under contemporary cosmic conditions. Rather than the nearly invisible, weakly interacting material we observe today, early dark matter appears to have participated actively in cosmic construction processes through mechanisms we're only beginning to identify. Perhaps dark matter particles could interact with each other through forces that operated only when their densities reached the extreme values that characterize the early universe. These interactions might have enabled dark matter to self-organize into complex architectural patterns that served as detailed construction blueprints for ordinary matter to follow during galaxy formation processes. As we reach the end of this cosmic journey together, remember that Webb's revelations represent far more than distant astronomical discoveries. They're showing us that we inhabit a universe of such breathtaking creativity and elegant complexity that each new observation rewrites the very foundations of what we thought possible. Tonight, as you drift towards sleep beneath the same starlight that has witnessed the entire epic of cosmic evolution, carry with you this profound truth. You are made of the very elements forged in those ancient stellar furnaces Webb observes across impossible distances of space and time, connecting you intimately to the universe's most magnificent creative achievements throughout all of cosmic history.